flew all the way from Luxembourg to see me. From Las Vegas. Thank you. We good? Okay. Thank you and welcome everyone. My name is Jacob Torrey and my co-speaker Sergey Bratus unfortunately could not be with us. But this is our work we just finished up for DARPA I2O. It's called Crema, which is a LangSec-inspired programming language. So we're going to go through kind of the problems and kind of the LangSec kind of theory about what those problems stem from, how to propose a solution. We're going to talk about Crema specifically, which is one kind of piece of that solution, and then talk about some of the results we found in the paper that's actually out in the IEEE Security and Privacy Journal, and then some other kind of interesting stuff before we wrap up. Because this is a very mixed audience, and this can be very basic in some fields, but also quite advanced in some of the more theory stuff. If you have a question at any point, please just raise your hand and jump in if something is unclear. I gave a talk here last year, and I said the same thing at the very beginning, and I didn't get any questions, and I stopped partway through. I said, any questions? I still no questions. At the very end, any questions? No questions. I said, okay, well, see you at the bar. And everyone got up and lined up to ask me questions that they were too embarrassed. So don't be those people. Please just ask. So basically, in a nutshell, programming languages provide more computational power, or more expressiveness than most programmers need. And so LangSec has shown that this excess, within that kind of skin around the orange, is where you have these weird machines, verification difficulties when you're trying to formally verify and prove out your software, and then also a state space explosion when you're trying to do program analysis. So we're hoping that by providing a language that forces programmers to more accurately express their intent and to basically kind of right-size the programming language to most tasks, we'll be able to show some security wins. So I work for Assured Information Security out in Colorado. I lead the computer architectures group. This is actually kind of an aside for me. Usually I'm doing hypervisor research or operating system security. And Sergey is a professor out at Dartmouth. He's one of the kind of visionaries behind the LangSec field. He's the chair of the LangSec conference out at IEEE. But unfortunately, I had to miss it last minute. But you can reach out to both of us on Twitter if you have any questions or you want to get interested in the LangSec dialogue. There's a great mailing list that's quite low traffic, but very, very interesting. So a couple definitions, just so we kind of all know where we're on the same page. So Turing complete, basically if a system, if a program, if a machine can simulate the widely known Turing machine, so you have a tape with input, output, and then you can read through it. Basically, computers today are finite physical implementations of it. So technically, a computer is not a Turing machine because eventually the heat death of the universe will cause it to terminate. And also, it's not infinite. But for all intents and purposes, you can think of a program kind of as simulating that. And Turing completeness shows up in some of the most bizarre places. So Sergey and Julian Bangert showed that the Intel memory management unit itself is Turing complete. So without ever executing an instruction on an x86 CPU, you can actually simulate any program or any Turing machine just by setting up and triggering these memory errors at the right time. And the interrupt logic is so complicated that you can simulate any Turing machine without executing a single instruction. It shows up all over the place, and it's kind of a very nasty thing to try to work around and analyze and verify because of the halting problem. So this is kind of a classic problem in computer science that is provably undecidable in general to determine if kind of any program will halt on a given input. And there's a proof for this using Cantor's diagonalization, which we won't get into, but basically you run into this issue once you get to a certain class of computational power. It's also known kind of as the undecidability cliff. So the more complicated an environment you have, the more difficult it is to analyze. And eventually you kind of reach this cliff where everything more advanced than that just kind of falls off the cliff and it's kind of impossible to recover from. This is kind of more granularly codified in the Chomsky hierarchy, which just shows kind of here, you'll see formal language classes and then the machines that can basically represent them. So you have very, very simple finite state autonomous finite state machines that can recognize and accept regular languages. And then you go all the way up to context-sensitive, context-free, and then all the way up to uncomputable. And so you'll see here that basically there's levels of complexity, and then also there's machines that can accept it, and then the actual grammar class itself. So LangSec in a nutshell. This is a very long, but essentially, when you handle input in kind of loosey-goosey ways, you're opening yourself up to a whole set of problems. If you were to formally verify and parse your input to the same degree of certainty that a compiler does, for example, if you leave a semicolon off on your compiler, it'll throw it up at you because you didn't meet the formal grammar for whatever language you're programming in. Most input handling for data doesn't have that same level of exactness, and because of that, you get a whole bunch of these kind of weird machines, which are essentially virtual machines of the Java VM, not the VMware VM type, that run some weird instruction set architecture that's defined by your data. And so you can turn data to drive execution. And so with LangSec, if you take software that basically formalizes the specification for the input language and rejects anything outside of that, you're going to basically remove a whole class of attack. So that was great. So basically, we built the internet on faith that developers will properly sanitize their inputs. They'll think of all possible kind of edge cases, and they'll properly correspond and work against that. And then we've trusted them to the full power of Turing completeness. It's kind of like giving your 16-year-old kid who's never driven before a Ferrari, because that's pretty much the most powerful car. And why would you want anything less powerful? Why would you give them an Accord? And between this Ferrari and all of the breaches we see kind of on a day-to-day basis and everything coming out from Project Zero, maybe that faith that we place in developers might have been a little bit misfound, especially since the large majority of tasks don't require a Ferrari. Just commuting to work doesn't require a Ferrari, whereas maybe driving on a track does. So this is trying to right-size down the language to something that maybe will make it a little bit harder for programmers to shoot themselves in the foot. So this is some of Sergey's kind of thing where you have code that meets input, the code goes crazy, and then it elopes beyond your wildest expectations, and it's very fitting. We are in Las Vegas, and here we have, I bet there's probably an Elvis wedding in there as well, which you could probably say return-oriented programming would be that. So essentially, with return-oriented programming, your data, which is return addresses, ends up being kind of an assembly language for this virtual machine, and you're able to derive execution flow from data. The other issue with this is that static analysis are very, very difficult to kind of, in a general sense, kind of classify and then actually prove. And so we're going to talk about that, some specific examples a little bit later. But essentially, you get to the point where if you have two parsers that should recognize the same input, it's typically undecidable whether or not they're the same. And so you'll see this issue with there was just a Bitcoin bug in the Bitcoin protocol where they had separate interpretations of the ASN1 standard for certificates. And so if you were running it on a 32-bit system, you would think the transaction was invalid. But if it was a 64-bit system, you'd think the transaction was valid. And so that would create these kind of splits and forks in the blockchain based on the CPU architecture. And so being able to verify that basically both versions on both systems were running kind of in sync is pretty difficult to do. And so that's where you get these weird machines, which are kind of these strange computation of virtual machines. That kind of comes from that surprising Turing completeness from the memory management. It shows up, the BGP routing protocol is actually a distributed Turing machine. You can actually program the worldwide BGP network by making certain requests. You can set up like a circuit and then kind of from that build all the way up to a distributed machine. And so you kind of, it's very, very easy to end up in Turing completeness, which is kind of strange because they have all these languages like brainfuck or boolfuck, which try to say, oh, we're the smallest Turing complete language, which you want to be, I want to see the biggest language that's not Turing complete because there's a whole host of kind of problems that come with Turing completeness. So basically, this is a great quote. I'm just going to say, the illusion that your program is manipulating data is powerful. It's an illusion. The data is controlling your program. Your input is driving execution. And maybe not necessarily in the sense that, the CPU is running your data per se, but it is driving execution flow. And any input is a program. And so this is where I talked about that if you have a complex data format, how do you distinguish between something like a Java bytecode or a ROP bytecode and then your actual proper data format? And so you have these weird machines that jump up. They're basically virtual machines that execute this complex data format, and they derive execution. And so one great example of this is the PDF spec. PDF spec is very, very complicated. It's actually possible to make a PDF that has a cyclical reference for length. And until they put in a special edge case for this, you could actually send someone a PDF that would just loop forever and then crash. And so PDF spec is very, very complicated. And so it's essentially, it has the ability to flat out just embed JavaScript and other code into a PDF, which is a terrible idea. So at that point, what's the point of having all this other stuff? You're already letting people write code. Why bother basically make it really easy? So basically there's a gap now, right? So we've shown that basically it's pretty scary out there, but a lot of what we need isn't necessarily require all that kind of scary world. And so there's a huge gap between what programmers need for most tasks. So I would say many tasks you probably want your program to terminate, or at least generate input from or output from input. And so typically you want your program to kind of have some bound on its execution. There's a few examples, counterexamples to that, which I'll talk about later. But there's a whole bunch of things here that get in the way. So there's a lot of CPU features. There's a whole bunch of crazy programming language stuff. So like the the %n, the %s. There's a whole bunch of format character string weirdness, and then also optimizing stuff as well. So you can bring it all the way back to reflections on trusting trust, where you have all these layers of kind of abstraction. And so what we're trying to do here is, if you create your data specification as strictly as your code specification when you're writing your code, you should be able to kind of have predictable computation and be able to really cleverly analyze it. So our approach is to limit the power of the processor, or in this case the execution environment. I'm actually talking with some folks from Intel about kind of reusing some CPU flags to be able to actually create a limited kind of execution mode. Kind of like ring 3, you could make like a ring 4, which is then kind of computationally limited, which then gives you better predictability, and then it's basically a language that's deliberately not Turing complete. And so it's going to require a little bit more thinking from the developer standpoint, because they need to figure out exactly what they're trying to do, and they can't just kind of use a catch-all. And so I'll talk about a bug in Sendmail that Mark Dowd found, which basically showed that a programmer was not necessarily thinking about the full intent of what they were trying to do. And because of that, they had kind of some extra edge cases that allowed remote code execution. So our goal is we want to make something that ends up being accidentally Turing complete. We don't never want that to happen. We're trying to make it so that the programmer has to think through what they're trying to do and make it such that it's never going to end up kind of in this undecidability cliff. We're going to talk about least privilege principle as opposed to computational power. So one of the interesting things about this is typically when malware first came out, it would be running in user space, and your anti-malware would be a kernel mode driver. And so it can kind of look down. It has more power than the malware, and it can pretty easily find it. So what did a lot of malware people do? They found ways to hop up into the kernel, and now they're kind of playing on the same space. And so now there's AV and next generation, whatever FireEye stuff that runs in hypervisor land, but at the same time, now it's a matter of time before malware starts hopping up into VMM. This is the same thing with reference monitors and programs. Right now, you might have some reference monitor that's checking a program as it's executing to make sure that it's not doing something bad, but that's operating in the same kind of computational privilege level as the program it's analyzing. And so you can think of a reference monitor as essentially an automaton that recognizes a series of inputs from events, basically. So it's watching the program, and if it starts seeing these events that it shouldn't recognize, it can use a prefix and say, all right, everything past that is bad, and then it can halt the program. If you had a provably halting execution, you'd be able to do a much stronger, both prefix and postfix are kind of all encapsulating, and you'd actually be able to run a computation, see if it matched some malicious characteristic, and then actually roll it back as a whole because you have kind of this computational transaction. So Meredith Patterson, who also couldn't be here unfortunately, had a pretty good quote. So your CPU has to be able to perform arbitrary computation. The echo request doesn't. So allowing like basically a full virtual machine to run anything in your network stack is probably not so good. And you sometimes see this stuff, especially with actually ASN1 parsing, which is used a lot in HTTPS, TLS, SSL, where you just have these very kind of arbitrary computations and very, very complex computation that need to be done just to parse input. And so your CPU has all this power, and programmers are kind of letting it at it. So that's a pretty poignant quote. So this Sub-Turing programming language that we're going to develop, where I'm going to magically, it's like a cooking show. We're going to talk about what we're going to make, and then in the next slide, it's already going to be made. So basically, we want to make it really, really hard to express what's hard to analyze. So from a program verification standpoint, bugs are always going to happen. Developers are not bad. They're not, dummies. They just, sometimes you make mistakes, you have deadlines, you got to work, and you got to do your thing. And so a lot of times also you have feature creep, or you were told that this is just going to be a prototype and it's going to be scrapped and then rewritten in beautiful code. And so you hack it together and they're like, oh yeah, let's push it to production. We're good. So people who are chuckling have probably worked in similar companies. So you want to basically compile this program to an execution model where things that are hard to analyze or ambiguous are kind of hard to program too. And we wanted to make sure that it can resemble C well enough, because programmers don't fall from the sky. They have to learn. Making this language open source and DARPA investing in this doesn't make sense if only 3 PhDs in the world can program. I don't have a PhD, so I'm one of the people who is not a PhD that can program in it. But we really want to make sure that it's kind of easy to use so that you could actually start including it in at least portions of your program. So apparently, crocodiles, I learned this, don't turn around. So if you imagine a processor that never went backwards, so you have no loops, you have no Turing completeness, and then you combine it with basically an upper limit. So Captain Hook would have a much easier time evading from a bounded execution crocodile. Apparently the crocodile's name is TikTok. I learned that today. So just kind of an aside there. Sergey thought that had to be included, so there it is. So basically all these questions and concerns is basically, all right, so we've been developing software for a very long time, and it seems like there are some edge cases that the software has been kind of able to withstand the test of time. But there's also a lot of cases where that clearly hasn't been the case. And so we started a DARPA seedling under I2O, which is their kind of information operations group. We tried to figure out what the minimum kind of cover set for the majority of programming tasks were. Obviously, we knew we couldn't do everything, but we wanted to be able to figure out, okay, what are most programming tasks do? And a lot of those are basically parsers, or what we call transducers. They take input from some format and provide output. That could be something like a USB mass storage driver. It takes input from the USB bus, which is basically data being loaded into memory mapped I/O space. It parses that into essentially SCSI, and then it passes it off to another driver, which takes SCSI to VFS, and then VFS to FAT or EXT, and it's just chains of parsers that all themselves should terminate, and you can kind of put a bound on it based on some polynomial function of the size of the input. So if you kind of basically make this programming language provably terminating in countable time, so that's what's known as Walther recursion, you have no issues with the halting problem, so you've been able to kind of sidestep that huge issue with a lot of verification and programming tasks. The programming language forbids unbounded loops and unbounded recursion or co-recursion, so that's if you have function A that calls function B and then B back to A, so that's kind of a trick that you might be able to break out of, so you explicitly prevent that at compile time. We wanted to make sure it was very usable and embeddable, so we actually emit LVM intermediate representation code, so you can link to it and call from it and optimize it the same way as any of your other source codes. So if you're writing Xcode and you're writing a parser, say in a program you're writing for OS X, because that uses CLang to compile down to your intermediate representation, you'd be able to write your parsers in Crema and have a pretty high degree of confidence in them, and then just kind of call parse data from C if you need to do some crazy graphic stuff. And we tried to make it easy to develop in a pretty small learning curve. This is still an ongoing effort, and we're working on getting some follow-on to make it even more easy to use. People I think C is a great language to learn and it's very easy, but it seems like the common trend in computer science programs is that Python or Java is an easy language, and so we're trying to make it as easy to learn as possible, just because if the developers who are maybe struggling to learn and understand the nuances of C are learning Crema, at least they have less rope to hang themselves with. So obviously it's not the right tool for every task. There are some programming tasks that just flat out require full computational expressiveness. So anything with unbounded looping that requires unbounded looping. So imagine if you had your OS scheduler that you had to put a bound on. So your Linux system, you boot it up, and then after 5 minutes, it just forcibly shuts down because after that, you're done. You're out of time. So that would be pretty frustrating. It'd almost be like running XP when they shut your system down when you have an update without telling you. Oh yeah, we're not going to save your stuff either. Don't worry. So, and then also you have a lot of kind of server listen loops. So Apache has this loop that just listens on a certain socket and then forks off or worker threads essentially when it gets a request. Those worker threads, what they should do is probably be Sub-Turing. You don't want a website to take forever to render, but the thing that's listening there should basically go on and for a very long time. And then a lot of user-driven programs, the UI side of it, typically are multi-threaded anyways, because you have your UI thread that allows the user to click on a whole bunch of stuff, and then the background processing. And so the background processing would be something that you'd want to be bounded, but the actual, waiting for the user could go on for a long time. And you can actually see this model in the real-time fork of Linux. You have kind of your tight loop, and then you have these little tasklets in the kernel. You also see this in Windows kernel programming. You have like a top end and a bottom end, interrupt handler. And so basically the top end says, there's a lot of work to be done here, but a lot of people are waiting for me, so I'm just going to queue it up for later, figure out what's the least important stuff, and do it later. And so you kind of already have this kind of system set up. It's just a matter of really limiting those parts that are already could be limited. And since Crema, is very easily to embed, you have a lot of parsers and data analysis methods in LLVM, and you can really compose this really well. Like you can take a Crema file and a C file and compile them down to the same binary. So it's strongly typed, a C-like language. As I mentioned, you can use the LLVM to call into or be called from other languages. You can have structures that can pass back and forth. And it can express anything that's known as a parser or a transducer, which essentially converts input from one format to another, which seems like a very, very small use case. But if you think about how you organize your program, it's actually a very, very common kind of design pattern. These transducers or parsers basically should take a polynomial time function with respect to the input length or the input complexity, and that should not be undecidable. And so this is kind of how you are able to calculate the bounds in real time. So this is Crema. It doesn't look too crazy. Essentially, we have an array of ints called 100. So the Crema seq basically generates a sequence, like in Python, with between 1 and 100. This is the FizzBuzz programming challenge. I'm sure you've all seen it in some interview or Joel on software. And then basically, you're just for each looping through it. So this is a very straightforward, FizzBuzz right here. It looks pretty similar, other than the kind of ugly int print and string print separate line thing, but that's something else we're trying to clean up a little bit. But for the most part, it's pretty kind of approachable. Some of the other kind of Turing complete or sub-Turing complete languages out there that have been built in the academic world are almost like unparsable by people who are just normal developers. So we tried to make it something that's pretty approachable and pretty easy to learn. So it supports, your typical stuff: structs, arrays. The lists and arrays automatically scale, so you can just append stuff to lists if you need to. Obviously, you can't append stuff to lists that you're iterating through, because then you can just keep appending to the next one. But memory is automatically managed for that. You have all your normal Boolean and bitwise operators. Your main looping construct is for each. And if you just want to do kind of a constant time, you can just throw in a sequence generator. So CremaSec 1 to 3 will generate 1, 2, 3, so you can make an easy kind of loop in that way. So it's still pretty young. We spent about maybe 4 months working on it. We're looking for input from anyone. This is kind of its first release out to people who are not academic and who might actually consider using it or have features they miss. So we have some future work that we want to do. Object-oriented classes, that kind of stuff is really good for representing kind of hierarchies of data and functions. What we think would be really interesting is actually integrating a parser generator, kind of like Lex or Yak, but specifically designed for not necessarily code, but for data, into it as the only method for reading input. So imagine if you took C++ and you removed cin, and you have to specify basically a format in, like, say, BNF for what you're trying to recognize, which would then automatically generate something that would reject any invalid input. Right there, you'd basically make C++ like bulletproof. And so we're trying to figure out a way that we could be able to take that so that you have to think about what you're trying to accept. Because typically you think about what you're trying to accept, and you don't try to think about what you're not trying to accept. And it's all those edge cases that weren't in your mind that an attacker will be able to exploit. We want a much stronger standard library. Programming in Python is like so easy because they have everything for you. It's like, or PHP, you just add like what you're trying to do and underscore what's underneath it, like write a compiler underscore, and then boom, it just does it. So we also want to do some cleaning up. So right here, kind of the int print and string print, it's kind of ugly. We want to make some kind of syntactic sugar to really clean that up. And type conversion is a little ugly right now too. So here, if any one of you guys are theoretical geeks, basically we took the formal definition of a Turing machine and we re-implemented the transition function, which is basically the same except that it can't visit the same state again. So essentially, it's going to run out of states. And so basically, it's exactly the same except that Q prime is a new set of states that has the current state removed from it, so it can't loop back to itself. So it's same Turing machine model. If you guys are taking pictures of the slides, I'm going to post them online if that saves you some effort. But and the video. So, all right. So this is very pretty when you typeset it in LaTeX, which is probably the only reason to write in LaTeX because it's very pretty. But what does it actually mean? So imagine a CPU that can only execute forwards. So say to higher memory addresses. You'll never be able to jump back. And so if you have that program that you write and you line it all up, from the first instruction all the way to the last instruction, that program will terminate because eventually you'll hit the end of the program or the end of your memory, your finite memory, and it will terminate. So you can actually compute how long that's going to take. And that basically enforces your bound on the state space explosion to verify if you're doing some program analysis. You just basically count the number of branches in between the start of the program and the end of the program, and that's the number of possible states this is going to terminate. Unfortunately, this removes all kind of powerful things like looping or function calls, which as a developer I kind of like. That would be really annoying to copy and paste your program. So this is this kind of theoretical model that we used in our paper to kind of create the formalism. This is not actually how Crema works. We don't put the CPU in a special mode. We just kind of do it at compile time. But think about how this is equivalent to Crema as we go forwards. So we kind of introduce this work called basically just-in-time loop unrolling. And so you imagine that you have your program, which is kind of this abstracted model of a program that has the loop, kind of like the body of that loop abstracted. You have all the functions that are there, kind of like pieces. And then you just-in-time assemble it once you know the length of your input. And so say you're going to loop through your input twice to do something. You can then basically go in and you can unroll the loop twice. This is not actually happening. This is really inefficient. But for the formalism, let's assume that happens. So you're going to have your abstract program. You're going to do just-in-time kind of compilation or loop unrolling and function insertion. And then you're going to end up with a very, very long and inefficient forward-only execution program, which then you can formally verify. And then you can basically put in kind of random input lengths if you'd like to kind of do some analysis on an abstract sense. Now, this supports Walther recursion, which essentially is, as long as you can compute how many loop iterations there are as some function of the input, this model with the just-in-time loop unrolling will be able to support that while still running in that very, very constrained forward-only execution model. And so, essentially, you're doing the just-in-time unrolling before you're running the program, and then you're doing your verification afterwards, so you can still have that very pleasant kind of bounded space to verify, but you have a little bit more power as a program. So your program analysis will operate on the forward-only execution, but when you're actually developing, you're kind of in this kind of play abstracted world, which is more powerful than the forward-only model. So, I kind of mentioned this, but Crema CC, you can have it output a program, like a binary for whatever platform you're on. Since it's using LLVM, it can support x86, 64-bit, ARM. It can run both just-in-time compiled down to whatever platform you're running on, or also it can be interpreted. But then also you can have it output as this kind of LLVM assembly code, which is an intermediate representation, and then you can kind of embed it in other stuff. So the ideal would be to use Crema kind of right off the bat for anything that's input-driven or parsing, and then you can use your existing language and kind of deal with that kind of cleaned-up data that you've already kind of got from Crema. You can call into other languages, but that will break your guarantees. If you call like while1 from C, that's obviously going to break those guarantees. And the nice thing with LLVM is that it already has a huge tool chain of compiler optimizations, verification tools. So CLE we used in our paper. There's also some of the stuff that does the static analysis in Xcode, the CLang. And so there's a lot of tools that kind of just pick up this, and once we're in that format, can do some optimizations as well for performance benefit. All right, QMail. DJB is generally considered a very competent programmer. He wrote a mail daemon called QMail, which was designed for security, and he basically, I think it's one of the first bug bounties I've seen. He basically said, I'll pay out of my own pocket, kind of like Donald Knuth did with his, if you find a typo in my book. He said, I'll pay you, some amount of money if you find a bug in it. He's had this open for years, and there's been one award, which was fairly minor. And so it's been generally standing the test of time. Halvor Flake, or Thomas Julian, and Julian Van Egg have basically been using this back and forth in conferences as targets. Basically, how would we use automatic exploit generation? What tools are needed to get automatic exploit generation to the level where we'd be able to actually target something like this? And so Julian has basically these kind of like core requirements of things that we haven't yet solved to be able to get automatic exploit generation to be just actually automatic exploit generation, rather than, I know there's a bug on this line and it's this type of bug, why don't you just figure out the sled for me? DJB actually kind of knew about LangSec before there was a term for it, so he realized that the parser that was network facing would be the attack vector, and so he actually wrote that to be in a separate process that uses a very simple flat file format to communicate with like the mail routing and all the other whatnot. And so the parser is highly isolated, which also makes it really easy for us to analyze, because we just analyze that part with having to worry about all the mail stuff. So what we did is we took that parser, we ran it through CLE, which is a symbolic execution engine that targets the LLVM intermediate representation. And we kind of gave it like timestamps, like, all right, let's run it for 30 seconds and 1 minute or whatnot. And we just wanted to measure kind of the code coverage, and then also we ran it for a while until the SMT solver started failing because the constraints were getting too difficult to solve, and we measured some running time. We then took that same parser, we re-implemented basically line for line in Crema, and then we redid the same analysis to see, all right, if CLE knows that the program is being run and it's going to be bounded, it might be able to make more kind of assumptions, and some of those constraints might be easier. So you'll see the red dots are the number of states run, and then the blue dots are the restricted ones in Crema. And so this is based on the length, a symbolic length of a string in a certain data structure. And so as you go from, like 4, 5 characters up to 9 characters, you go from just under 1,000 to 7,000. So you get some pretty high growth in the number of states it has to visit. And for each one of those states, it actually has to go and create all these constraints, send them off to the SMT solver, which is NP complete, and then it has to wait a long time, and eventually actually will run out of memory and crash. Restricted paths, 45 is a little bit more manageable than 7,331. You can also see this as a line graph, basically the number of paths it had to explore, and then this is time bounded. So after 10 seconds, we basically quit the program to see how many states it had kind of identified to be traversed. And you'll see that it grows much faster for the normal versus bounded. And then the last one, you'll see here just the instruction coverage. It covers a lot more of the program right off the bat. There are some weird things about how this instruction coverage is measured. The program Hello World, if you run it in CLE until it completes, it will only say about 60%, just because there's so many strange, weird things in printf that require a string of a certain length or certain kind of quantifiers and controls. And so the reason it's capped, it's mostly the fact that it's just running into these library functions that it just can't explore because there might be some previous constraint. All right, that brings us to Sendmail. So we're talking about email a lot, I guess. So most of you guys know Mark Dowd, kind of like a genius. He found this bug actually in 2003 that in Sendmail. So there's a very simple parser just to make sure that your email address that had matching parentheses and matching angle brackets and they weren't nested or kind of confused, and to make sure the email address was valid. So basically it took an input email address and then would output one with closed parentheses if it needed some. It reserved space in the output buffer to make sure there was no overflow, so it actually reserved extra space for those closed parentheses, and since it didn't allow nesting, it only recovered 2. Unfortunately, he found that a pointer they were using rather than a length, they were using pointers arithmetic. They found that it was failed to decrement, and then it caused an overflow. And so this basically got a remote code execution on Sendmail. Hulver then used this as basically a verification / automatic exploit generation problem, is how could we have found this bug automatically? And so that was kind of an open challenge from Hulver. And then in 2012, Julian basically showed how you would use an SMT solver to find that specific bug. The only issue is the analyst who was basically writing that verification question had to know about what the bug was going to look like, because if you look at the source code, it's just a while loop, and you're not really sure that if it's iterating through the loop or if it's waiting for some time condition or what. And so it's very hard to generically see the badness on this unbounded loop. It was a while loop. If the programmer had gone a little bit further and maybe put in a for loop or a for each loop to kind of loop through that input buffer, then the verification problem would have been a lot easier, because it would have detected that it was looping through and then it was looping past the end of the array. And so this is kind of another example of something where not necessarily the Crema language itself, but that idea of forcing the programmer up front to really kind of figure out what its intent is, his or her intent is, and to implement that as clearly as possible makes analysis and verification much easier. And by basically making it very, very difficult to put in these vague and ambiguous terms, you're going to get very few hard to analyze problems. How can I help you? So basically, we would allow, you could limit the bounds to loop. So that means even if someone did find this exploit, they'd be bounded to how many loops basically it had left through this parsing function. Programming verification tools would be able to detect if the program was outside its bounds. You'd have a reference monitor that would be more powerful and it can actually recognize some of these overflow conditions. And then the programmer's intent is more naturally expressed, as I talked about. A while loop is kind of a catch-all to loop, but it's kind of very difficult. I mean, you see while loops do while 0 all the time. And so you have that on one scale, which is basically just to wrap up some of your kind of C scope. And then you have while 1 break in some other programs. And so then this is a perfect use case. I mean, basically this parser that on all circumstances should terminate. You don't want to have an email address that will run forever trying to figure out where it should go. So Crema is useful reducing the length of a rope programmers can hang themselves with. Even if you do implement a bug and someone does find a way to exploit that, they're kind of naturally capped at whatever running time left. So you think back to the TikTok crocodile. A crocodile that can only run 1,500 paces or whatever it is a lot less scary than one that can kind of run forever. A computationally bounded attacker is a much weaker attacker. Yes? So, yes. It will, so basically you are writing so a sorting loop, right? You're going to go through, a maximum of, say, whatever the asymptotic running time is. to maybe sort some input. And so you're not necessarily saying this is the bound. You just need to be able to express the code in such a way that, say, maybe reads through a string and looks for certain characters. That's going to run. I mean, so we're assuming finite input, right? So So you can think of the halting problem, right, is trying to figure out if a program will terminate on a given input. And you'll be able to essentially have that finite input a priori. Crema doesn't count how long the input is. That was like the formal model that was kind of just for the math. But what we'll do is basically it's very hard, well, hopefully impossible to represent a program that will be able to go through beyond the length of that input. And so if you have a program that accepts input and you say, yeah, wait until the null terminator, and you never send a null terminator, Crema will run forever in that regard because you're sending essentially an infinite loop or an infinite input. But once it has everything read in, and you can also think about this as fundamentally you could put in some kind of symbolic variable for that length of input or that input at some point. And then you could basically require them to put all their input in a priori, kind of as like, say, command line arguments versus waiting. And then you can do, you know, finiteness checks. And then you can insert that in a more concrete value. So you're basically replacing that symbolic size with a concrete size once you get it. And so counting the length of the string, it doesn't necessarily mean how long it is. It just has to be finite. And that you can't represent in Crema a unbounded loop on, say, an input of any size. And so the counting doesn't necessarily matter unless you're doing analysis. It more matters that you can't represent a program that will be able to take one input and then possibly run forever. You just can't represent a program that does that because all the programs are using what's called Walther recursion and are halting. There are some programs that would terminate that are not Walther recursion. They can't be basically proven to be terminated, and so Crema can't actually represent those programs. So there is kind of some class of some problems that would terminate and could be sub-Turing complete, but because our recognizer can't recognize them as such, they're explicitly kind of fail-safe. And so in a sense like that, where you might have some of these edge cases where counting might be a challenge, that would probably be a system, an example of one of these outside of Walther recursion problems that it would just kind of fail safe and just not recognize. Yes. You have to give it a finite input, yes. And so that's why as the Apache, yeah, the program has to know how long it is, yes. All right, so it's open source. Thank you, DARPA. All the code, examples, documentation is up on crema-lang.org. We hope you check it out. We want you to hack on it, submit patches, start using it, give us feedback. Right now we know it's very limited and the standard library is quite shaky in the sense that it just doesn't let you do as much as, say, Python does. But we'd really like to say, hey, I will want to use it in this kind of project. Could you start doing some stuff more and, say, maybe more network parsing or whatnot? And then hopefully by using Crema, your software will be magically easier to analyze and safer. When I was at RSA, I think I counted magic in vendor pitches maybe 4 or 5 times that this vendor appliance magically makes you safer. So with that, are there any questions? Feel free to reach us out on Twitter if you have any questions, or if you have any questions now, or I'll be around throughout the week. So it depends on the complexity of your match, right? So a regular expression is a very kind of constrained input language, and so that right there would be very easy to put in to something like this. And so you'd be able to submit that. But much more complicated, so kind of beyond, so context sensitive or even higher complexity than that would not be, because representing and being able to take in these complex data formats and being able to recognize them would thus have to make it. So think about recognizing PDF, where you have fields that can point to other fields that can point all the way around in a circle. If you wanted to match on that, that parser is going to have to go through and it's going to keep going around and around and around. And so that will make your whole program get to the point where it's not going to be Sub-Turing complete.
Hi. Question first, then comment or context. Support for functional programming style. The context is we're developing a domain-specific language to support a variety of agent-based modeling. So we have a scheduling loop that handles when things execute. Agents do generally finite things within each step. And we're creating a domain-specific language to specify what the agents do and what they're capable of. And it turns out for application, we have lots of things that look like transducers, and we want to use functional programming style as a compact, sufficiently expressive way to describe what they're going to do. And so I like everything conceptually about what you're doing. I would like to be sold that Crema would be a useful tool for us to plug into our Java Scala stack.
Okay. So functional language, actually, we're working on another effort to make basically Crema more specific. So you could actually say this function is Turing complete and this one is not. And then how you actually verify software that's kind of mixed. So when NICTA did SEL4, which is a formally verified microkernel, they basically manually went in and categorized all the functions of their kernel and said these ones are Turing complete, these ones are not. One of the ways we're thinking about representing it is actually using continuation enclosures, which is a very common formal method. And so we're actually working towards integrating more and more functional paradigms in there, first-class functions, etc. So that's definitely something that I'm a functional programmer by myself, typically, and so that's something that I like to see as well.
Okay, thanks.
Sure. So the source code for Crema itself is C++, which is just kind of the native LLVM API. And then when you compile it, you get Crema CC, which is essentially uses very similar argument to GCC. You can give it a Crema file. It'll either output a .l file or LL file for the LLVM IR, or it will output just a flat-out A.out type binary. Sure. Yep. So that was one of our, when you go through and you pitch a DARPA program, they ask you to go through and find all the weaknesses. If you can find some way to basically inject IR or inject at the kind of, at that level, then you'd be able to bypass it, right? And so what DARPA's interested in is actually coupling this with Sub-Turing environments. So imagine FPGA that also kind of knows about that. And so that way, even if you're able to find some issue in the optimizer or find some issue where you can inject raw intermediate representation code into the JIT, you'd be able to still be bound. And so they're looking at FPGAs. They're looking at kind of restricted computational environments. That's actually what we're talking to with some folks at Intel about how you make a CPU mode. So my usual background is really low-level stuff. So figuring out ways for the x86 architecture to do things that it shouldn't normally do. And so we found a way to basically emulate a forward-only execution model. And so we think if we couple that, you basically set a bit in some ELF header basically saying this program should provably terminate, and then you'd be able to use CPU to basically prevent that breakout. But yes, very good question. That's definitely an identified weakness. Yeah, so this would not be any CPU modifications. This would just be, one of the other work I did was called hairs. It allows you to take a binary, fully encrypt it with AES, and then run it at native speeds with the key never in memory and the decryption decrypted instructions never viewable even to a compromised OS kernel. And so that was basically fully encrypted execution, but done with no CPU modifications. That was all done in software. And so using that same type of capability to be able to do that for this. So it'd be basically a Linux patch or maybe a thin hypervisor or whatnot that basically allows you to provide that without having to go out and buy all new hardware. That's what I like doing, is figuring out ways to like backport security to get it for legacy stuff. So moving forwards, we're looking at the Hammer parser generator done by Meredith Patterson. So we're actually working on a joint effort with them, well, proposed effort at least, to both formally analyze Hammer to make sure there's no implementation flaws in that, and then embed that right into the language so that when you're reading an input, you're going to give it basically a Hammer parser generator definition, and it will generate the code right then and there. So you will only be able to formally specify your inputs. All right. Thank you.